Hey cool worlds, it's David. Regular subscribers of the channel will know that a few months back we announced that we had an Exomoon candidate, Kepler 1625b. You can click up here to watch the original video, but you might remember that we tried to really emphasize that we were not considering this to be a discovery, we weren't considering this to be even a bona fide detection at this point. It was just a candidate object which emerged from our survey that we felt was interesting and warranted further investigation. You might also remember at the time that we weren't actually that enthusiastic about even really talking about the candidate at that time. And the reason was because, Exomoon is just, for whatever reason, it happens to be one of those astronomical topics that the media and journalists really love to play with, and they tend to sensationalize any little tiny nugget of news which comes out of our analysis. So we, definitively consider this to be a candidate, and yet we had this great fear that it would be misreported as a discovery or a detection. Was it released at this time? We would much rather, wait until we had done our homework and knew either way definitively. So, surprise, surprise, after this story came out, several news outlets, including some major ones, ran with the headline, "Exomoon discovered." And yeah, that was an annoying moment for us because we had really laid out as clearly as we could that that was not the case. Now, because there were only 3 transits or 3 eclipses observed by Kepler during the entire 4 years of its primary mission, we really didn't have enough data to make a confident assertion as to whether this Exomoon was real or not. And that's why we argued that we needed the Hubble Space Telescope to point back at this star, observe the next eclipse or the next transit, and hopefully confirm or deny the presence of our Exomoon candidate. Now, Alex, teaching my graduate student here, has been working on those observations, and in my spare time away from teaching and other projects, I've been trying to help out however I can. So I want to give you guys a little update about how this effort is going so far. So here's a composite image of all of the observations we took sort of stacked together on top of one another. You'll notice the image is quite small. It's only 256 by 256 pixels. Actually, the full possible number of pixels you could do is about 1,000 by 1,000. We actually deliberately only did this subarray so that we can actually read out the image a lot faster on board. The target, Kepler 1625, is that big long smear right in the center of the image. And you might ask, well, why is it smeared out like that? And that's because we actually pass the light through a grism, which I guess you can kind of think of almost like a prism, which spreads out the light into its constituent colors. Altogether, we collected 232 of these images, each of which constitutes about a 5-minute exposure. And these images were collected over 26 orbits of the Hubble Space Telescope around the Earth, each of which itself takes about 90 minutes. So that gives us a total of something like 40 hours of continuous data here. Now, because our target star doesn't lie in an ecliptic pole, then it will disappear behind the Earth periodically as Hubble goes round on its orbit, and obviously that's kind of annoying, but it's somewhat unavoidable. You'll notice that slightly above Kepler 1625 there is a very faint source which we think cannot really be contributing much flux onto the target. Further up you can see another star, that's KIC 4760469, which is a little fainter and actually serves as a really nice test case or comparison star for us. So the way we create a light curve is actually take each one of those images, we sort of draw a box around the target, and then we just sort of count up how much light was seen within that box at every exposure. So that allows us to build up 232 brightness measurements, which is our light curve. Now, when you create that time series of brightness measurements, it's really easy to see the big dip in brightness due to the planet passing in front of the star. But of course, what we're really interested in is there a second transit buried in there because of an exomoon? As wonderful and precise as the Hubble Space Telescope is, it is of course not a perfect telescope. There are known instrumental and systematic effects which sort of corrupt and introduce artifacts into these light curves that we look at. A classic effect is called the ramp or the hook effect, which is due to charge trapping in the charge coupled device, which actually takes the images. It's kind of the camera, if you like, inside Hubble. You can kind of see these hooks and ramps in this light curve here. This is actually our comparison star that I mentioned. And if I want to detect a very small dip, which is of order of 1 part in 1,000 inside this light curve, then I can't ignore these hooks. I'm going to have to actually correct for them. The classic approach to do that is to sort of fit an exponential analytic ramp function through it. We're actually taking a different approach. Me and Alex have sort of devised our own strategy. I won't talk too much about it, but it's really nice. It doesn't actually assume any formal parametric shape for what these ramps have to look like. When we apply this algorithm to our comparison star, it does a pretty good job of cleaning things up. We get residuals left over here of order of 600 parts per million, or ppm. You'll also notice the comparison star is really stable, which is good news. Its brightness isn't sort of linearly increasing in time or anything. When we apply this algorithm to the target star, Kepler 1625, we do even better, and that's just because this star is brighter, so there's more flux to work with, and we get residuals of order of 500 parts per million. To give you some comparison to the Kepler photometry, this photometry is about 3 times more precise than that observed by Kepler. So we're feeling pretty good about the precision that's coming out of this. So I think I should probably stop there, just because I don't really want to muddy the waters and make you think that there is something or is not something there in our light curve, because we actually haven't run our moon models yet through the full transit that we see. So it would be disingenuous of me to try and show that to you or to try and hint at things until we've really done our homework and our full analysis. I know you're probably going to ask about timeline. Well, when's that going to happen, David? When are you going to have that analysis complete? We're not sure, but we're thinking hopefully in the next sort of 2 months, maybe 3 months we can get that done. It's very difficult to predict an exact timeline for these things. But obviously we are, trust me, as enthusiastic as you to get this done as quickly as possible, but we really want to make sure we cross our T's and dot our I's and make sure we do a really clean job of this. So thank you so much for your patience and bearing with us as we work on this. I wouldn't say fingers crossed that we detect an exomoon, because as I said in my objectivity video, I think that biases ourselves. All I say is that fingers crossed we can actually find the truth, whatever it is, about this target. And given the data quality we are seeing so far, I'm actually feeling pretty confident we can do that. So I'll make sure Alex gives you an update in the new year, and hopefully we can let you know whether this moon is real or not in the near future. So thank you so much for watching, everybody. I hope you enjoy these videos, and if you do, make sure you click the subscribe button down there so you can get all the videos from our channel. If you have any comments or questions about Kepler 1625 and they're not too spoilery and I'm allowed to answer them, then I will do my best to answer below. I really appreciate all of you tuning in to check this video out, and until the next video, stay thoughtful and stay curious.